Hi, everybody. Welcome to our first Future in Space Hangout for 2021. My name is Tony Darnell from deepastronomy.space, and today we are going to be talking about finding exoplanets using the sun as a gravitational lens. I mean, this is awesome. This is just amazing. So, I hope that you get as much out of this as I do. But before I get going, I want to make sure I'd let you know that we are monitoring this on YouTube, Twitter, Twitch, and Facebook. So please leave us your comments and ask us questions, and we'll be happy to get to them. These hangouts are sponsored by the American Astronautical Society, who brings these to you periodically to showcase some of the work and the technology that its members are doing. So let me go ahead and bring up our guests today. Here we are. My guests today are Louis Friedman. He's the co-founder and the executive director emeritus of the Planetary Foundation. I'm very honored to have him here. Welcome, Lou. It's so great to have you here. Also joining me is Slava Turyshev. He is a research scientist at NASA's JPL. So welcome, guys. Thank you guys for joining us on this inaugural first Future in Space Hangout for 2021. So where should we get started? I mean, are we really talking about imaging exoplanets using the sun?
Tony, absolutely. First of all, it's nice to be with you here and with the audience on this wonderful event, the 2021. So I guess, why do we do that? It's not only because it's an exciting science. It's not only because it pushes all the technology that we have for space exploration beyond the limit and actually enhances the current capability, but because it is the current reality that we have to deal with. As you are probably aware, there is a renaissance going on in astronomy, and that renaissance is related to discovery of exoplanets that are nearby, they orbit nearby stars. And Tony, if you can show the first slide in the presentation.
All right, let me go ahead and put that up.
There are plenty of exoplanets we discovered recently for the last 20 years. So this is the fast-growing field in astronomy. Reality, by today, we have roughly 4,300 exoplanets confirmed. We have almost 6,000 planetary candidates. And out of those big numbers, we have roughly 164 planets that have a solid surface, and they may resemble our Earth at some point. Reality is that finding an exoplanet that resembles our own Earth, it's only a matter of time. So realistically, we will find this exoplanet maybe with the current fleet of space telescopes and maybe ground-based research. We will be able to find, but what do we do next? Travel into that exoplanet in the near future, probably it's prohibitive. So we are not talking about traveling there with physical spacecraft. Going there within, let's say, 100 years from now, probably will be still a challenge. But what we can do today, suppose the New York Times come out tomorrow with the headlines that the first exoplanet, first Earth-like exoplanet is discovered. What do we do next? So the challenge is really, what technologies do we have? Tony, if you can put the second slide there.
Okay.
And, here I'd like to show what we do to enable that discovery sort of renaissance. We have many space telescopes, and here on this chart you see several telescopes that still operational. Hubble, Kepler used to work and was a very productive spacecraft delivering a lot of interesting data on the exoplanet. TESS is currently operational, and a lot of recent discoveries on exoplanet research come from TESS spacecraft. Soon we expect to have James Webb and WFIRST flying. All of those wonderful, magnificent facilities will enable discovery of exoplanetary candidates. The challenge there, actually, these instruments will not see those exoplanets directly. They will see a confirmation that an object similar to Earth or maybe Jupiter or Neptune orbiting nearby star. So there will be no way to see those exoplanets directly because there are many challenges. Tony, maybe next slide. Those challenges related to really the distance. Tony, if you can put the next, yes.
There you go.
So size matters. So this is just for comparison. You see our own sun, which is a big orange sphere in the middle of that slide. and you see our own Earth, which is a little tiny rock on the bottom of this picture. So when we look at when we're trying to find an exoplanet, the light from its host star overwhelms the reflected light that we would receive from exo-Earth, because they're so tiny and they don't emit light; they just reflect light. Basically, that is the host star is transmitting. So whatever we have to find, we will have to look. It's like looking at like a firefly nearby the searchlight. So essentially, the searchlight is very bright, and you need to find a very little tiny light around it. So the size does matter. So also the distance. Tony, please, the next slide. The distance. This is a wonderful selfie that Cassini spacecraft took of all of us. You, me, everybody. So it's a selfie. We made a great selfie. Cassini looked back at Earth, and so this tiny blue sort of pale dot. This is us. So the challenge is really the distance and the size. So here we come. It's a diffraction limited. For those of you who are familiar with optics, we try to sort of design our instruments where diffraction limit comes into the light. Essentially, realistically, we are looking at the ratio of the wavelength that we use to observe and the scale of the instrument, the diameter or the baseline for interferometer. Now let me put some numbers out there. So Tony, maybe next slide. If I want to see our own Earth directly and to be able to resolve that object with just 1 pixel, and if that object is at roughly 100 light years away from us, I must have access to a telescope with aperture which is 90 kilometers. 90 kilometers, 90. It's the distance to the boundary of space is just about, it's about 100 kilometers. We are shy by 10 kilometers to the distance, to the altitude to the space, which is internationally recognized boundary of Earth atmosphere. For those of you who are familiar with Los Angeles, you see the Jet Propulsion Lab is conveniently placed in this picture in the middle, and then a point down south. So essentially the diameter of our telescope must be that big. And of course, it's not feasible to even contemplate building an optical instrument with this size, because the tolerances has to be on the wavelength scale. It's just not possible. Tony, maybe next slide.
Well, can I just? I don't want to leave this point for a second, if that's all right, because this is confusing to me. A 1 pixel image of something the size of the Earth, 100 light years away. When you say make a 1 pixel image, are you talking about resolving a disk?
I'm talking about resolving a disk with 1 pixel. So
within that pixel of a camera, yes, there would be a resolved disk inside that pixel. And in order to get that, you've got to have, and if it's 100 light years away, the size of the Earth, you've got to have you've got to have an objective lens that is 90 kilometers in diameter.
Correct. And my resolution will be just 1 pixel. We all carry
1 pixel per Earth. So that would be the resolution element. That's pretty amazing.
We all carry cell phones, right? And cell phones have sensors that are about 4,000 by 4,000 pixels, or maybe even larger. And so we have images of our loved ones and the nature of everything. We take pictures of hundreds or maybe million pixels in megapixel images. That's what we accustomed to. We're accustomed to have megapixel images of objects. Here, I'm emphasizing it's just 1 pixel of the object that we are interested in. And to get just 1 pixel, that's 90 kilometers. To have megapixel images, or maybe 100 by 100 pixel images, I need to multiply that 90 by the number of desirable pixels.
That's crazy. Okay, I wanted to get that point in because this is crucial to what you're talking about. All right.
Absolutely. Maybe next step.
Right.
So here, this is what we are capable of doing today. This is the largest telescopes we built on Earth. So essentially starting from multiple objects on the ground, starting like 100 years ago, like meter class, and then the wonderful Mount Wilson Observatory telescopes. And on the right, within the red circle on the right part of this image, you see now a European extremely large telescope that is now being built in Chile. And so diameter of that instrument is 39 meters. And so on the left, you see the sort of the artist impression of that telescope that is still being built. And we're talking about 39 meters. And this is what we have done on Earth. Maybe next slide, if you may.
Okay.
And so basically, this is why we just realized that if we will follow the progression of classical instruments, optical telescopes and interferometers, we will not be able to make direct images of exoplanet anytime soon before we visit with them. But here comes the help from nature. Nature actually giving us a very wonderful helping hand by providing the sun in our backyard. Essentially, sun is a massive body, and according to general theory of relativity, light that travels nearby a massive body is deflected. So essentially, the light, the wave of light, when it is enveloping the sun, it will be focusing, and so the light rays will be focusing at not at a point, but at a large distance from the sun. So because of the solar gravity, although it is most massive in the solar system, but it's still weak. So the angle of that deflection is directly proportional to the mass of the massive body. In case of the sun, the initial place where the light rays will start focusing and forming the solar gravitational lens, it's beyond 547 astronomical units away from the sun. So 1 astronomical unit is the distance between Earth and the sun. And the most distant, used to be planet Pluto is about 39 astronomical units. And the most distant spacecraft that we have launched in space, it's Voyager 1. I think now it's 145 astronomical units away. So potentially, we can have access to technologies. We have the technologies that may take us far away. In this image, in the center of this image, right, conveniently placed in the middle of that image, you see the spot called solar gravity lens. And because this image done
right here,
right there. So it is done actually in logarithmic scale. It's very convenient to have the solar gravity lens in the middle. But the x-axis, the horizontal axis, in powers of 10. And so essentially the nearby star, Alpha Centauri, is on the right of this chart. And so Alpha Centauri is 4.3 light years away from us.
Over here.
And so it's right there on the right scale. But you see the solar system, you see all the planets, and you see Voyager spacecraft, Voyager 1, Voyager 2. And so we have the technology that potentially can take us there. And so also we have now understanding how solar gravity lens works. And at some point, we had a wonderful workshop at the KISS. It's the Keck Institute for Space Studies at the Caltech. And Lou Friedman, it's all Lou's fault. Lou Friedman approached him and said, Slava, what do we know about solar gravity lens? At that time, I have published just one paper, kind of criticizing it, because if you consider the solar gravity lens for magnifying or using it for microwave radiation, solar plasma will be a main problem, because sort of dispersion in plasma will kill the images in radio waves. But for optical wavelength and studying exoplanets, I started putting some calculations together, and I realized that we just given a very wonderful help from nature. So solar gravity lens is the one that will enable us to make megapixel images of exoplanets, and then essentially, despite the presence of solar corona. Suppose you have access to not kilometers.
So one other point, I'm going to interrupt you, Slava, just make one other point different on this chart. I mean, you've said everything, and I just want to add this one other point. This is a logarithmic scale, as you've pointed out, and the distance to the solar gravity lens focus area is 547 AU, and beyond that, as you'll get into. The distance of Alpha Centauri, the nearest star out there, is what, 270,000 AU. And the furthest we've ever gone with the Voyager spacecraft over there on the left is 150 AU. It gives you the scale of the problem. We might be able to reach 550 AU, as we're going to propose here. We'll never reach 270,000 AU. not in anybody's lifetime that's watching this or even conceivable. So if we really want to look at exoplanets, this is the way.
This is the way, Lou. Thank you. And essentially, that was the revelation that once we start putting our heads together, we realized that not only that do we have the technology, the current technology that we have is enabling that type of travel, going to maybe 650 to 900 EU, up to 1,000 EU. We have the technology that can presently that can be used to take us there, and we have now a very good understanding how the lens actually works. Tony, maybe just a few charts, just flipping through the charts, and then maybe the next one I'll show what can be done. Now you are seeing the images of the Earth. We done the simulation on the left. The two original images of our own planet. The upper left, it's our Earth in black and white. The solar gravity lens. It's an interesting lens. It's not a perfect lens. It has, at least when we consider only the monopolar gravity, it has spherical aberration, and spherical aberration creates a blur. For those of you who are familiar with how the optical, system operate, so spherical aberration creates a blur. And in the middle of this picture, you see the blur that is created by that spherical aberration. And using modern techniques to remove that blur, called deconvolution, we can actually reconstruct the image. And on the right, you see how we can reconstruct the image of Earth. But look at the middle picture. If you kind of look carefully, you already see some continental lines without actual deconvolution. You see some sort of, some features on that planet. But then if you do deconvolution, suddenly we're talking about maybe 10-kilometer scale resolution, or maybe 20-kilometer scale resolution. And there we're talking about, continental lines on the exoplanet. We're talking about topography, weather pattern. We're talking about doing spectroscopy, and with spectroscopy, potentially we can look at the presence of methane, oxygen, nitrogen in the atmosphere of that exoplanet. So suddenly, our solar gravity lens, it's like if you're familiar with the telescope, with cameras like SLS cameras, traditional that we use for taking images. When you select a scene, you basically have it in a wide angle mode. You basically, once you select the scene, you wanted to take a picture of a person or a sort of a feature, you zoom in. Essentially, you reduce your field of view, you increase your magnification, and then in your finder, in the SLS camera, you see the feature that you zoomed in, very high resolution. So this is what SGL does. We use 1-meter telescope with the instrument called coronagraph. Coronagraph blocks the sun because we still need to block the solar brightness. Once we block the sun, we use now SGL as a zoom lens that will reduce our field of view, but will zoom in on the exoplanet, providing us with very unique features of the exoplanet. We fly 1-meter or maybe 2-meter spacecraft with a coronagraph at the solar gravity lens focal area. And because of the solar gravity lens, again, it's an interesting lens. It doesn't have a single focus. It has a semi-infinite focal line. And we don't need to stop. Once we reach that focal region, our spacecraft just coasting along that focal line and continue to take the images of the exoplanet. And we scan the image pixel by pixel and then collect the data and sort of deconvolve the image. So maybe this is all just to begin the conversation.
So Slava, I gotta go back to this slide. So right here, we've got something about the size of the Earth reflecting light off of its host star. And the light rays are between us and the sun is lying in between the exoplanet and us. And so the light rays come around the sun and are lensed or bent, refracted, whatever you want to call it, into this configuration that you have at the bottom of this graphic. And the focus is not a dot. It's not a point. It's not an image plane. It's a line. So all of these light rays, because of the weak lensing of the sun, is causing these lines to converge in what you're calling a focal line. Correct. And that focal line happened because of the size of the sun and the distance of the various exoplanets that we're looking at. That line appears 500 some odd astronomical units away.
That's correct.
Am I right?
It starts 550 astronomical units away.
It begins, and then as you travel away from the sun, you still can follow the focal line, and you still will be able to sample the image.
Okay, real quick. How long is this focal line? You see I'm drawing it along. How long is that in AU?
If there will be no gravity, if there will be no plasma, it goes almost infinite. But then there are some disturbing effects that essentially will sort of make it less optimal. So, but I would say up to 2000 AU, we can actually benefit from the SGL right there.
Oh my gosh. And so then what you get at the end of it is this image on the far right that looks like a ring.
Right. It's called
That's
Einstein
what you see.
ring.
That's an Einstein ring, and it's imaged and mapped into this ring are the details of the exoplanet, right?
Absolutely.
Okay. Now you're talking about launching a 1 meter scale space telescope out to this point to be able to see this stuff. Am I right?
Correct.
Okay, good. I'm on the same page as you now. I just wanted to make sure I understood it. And this, the image that you just showed us, is the middle panels are the
those Einstein
is the ring put together and mapped onto a sphere, and then following on the right panel, you've deconvolved it.
It's image reconstruction technique, right? To remove the blur and essentially to bring that original image quality.
That's right. And then so for people who know physics, if you've got a point spread function of some kind, you can deconvolve, wipe it across, and remove some of the fuzziness, and you get this really nice amount of detail. But you pointed out rightfully and also awesomely that even with this blurred image, you can still get albedo changes. You can still see some detail in there, continents, that kind of stuff.
Global spectroscopy, you can know, you can determine the presence of the gases that we now associate with presence of life. Like methane.
Okay, all right.
Tony, maybe step back to the previous picture. I want to bring one more point.
Okay.
Exoplanet, which has the diameter of roughly, if you take our Earth and put it at 100 light years away. So the diameter of our Earth is 13,000 kilometers, roughly. So solar gravity lens compresses the image of that exoplanet to a cylinder with a diameter of roughly 1.3 kilometers. So we need to position our spacecraft within that image of 1.3 kilometers in diameter and travel within that image and collect the data. That's basically a few more numbers for you to appreciate. It's the image size of our Earth. It's 1.3 kilometers in diameter. That's what we need to place our spacecraft.
And the reason we need this, the reason that this is such a big deal is because we cannot resolve something the size of the Earth very far away without something ginormously huge, 90 kilometers just to get a 1 pixel element resolved. What about things closer by? What about closer exoplanets? Can we just build a 30-meter telescope or a GMT and image and directly resolve? Because I think I've heard that they're planning on doing that. Am I completely off right base there? Maybe not Earth-sized planets, but other exoplanets.
Direct imaging. If I go to the maybe the closest exoplanet in Alpha Centauri, we can use new techniques that were developed to detect its presence. But to resolve it directly and see sort of multi-pixel image of that object, it's not possible with classical instruments. With techniques, telescopes, and
not even for the nearest star where you get a resolved anything more than a pixel of a planet. So,
regardless of the size we can build here, I mean,
right? And the example that Slava uses to say 100 AU just emphasizes the fact that by biting the bullet and going out to the solar and using the solar gravity lens focus, now you can image not just the nearest planet in the best conditions, but you'll have hundreds of candidate planets that you'll be able to image with that technique. So it opens up basically the galaxy of exoplanets to be looked at.
And how many pixel elements would we get out of that arrangement?
Basically, the closest exoplanets will provide us with almost megapixel images. Like our
megapixel images. Wow. Okay,
megapixel
so
images for the closest exoplanets, let's say from 4 to maybe 10 parsec away.
okay, so this kind of an image is real. This is what you're really talking about, a multi-100,000 or multi-thousand pixel image
exactly.
of an exoplanet far away.
So suddenly that topic that used to be a science fiction, suddenly we are now operating at the level of fluxes, photon fluxes, and computing realistic signal-to-noise ratio, designing an instrument, and so we have all the important tools to really use that lens as a part of the optical system and design a spacecraft, design a mission, and data collection strategy that will enable us to bring that image back home.
This is incredible. So explain to me what I'm looking at here. These two.
The first slide on the left, you have a regional image of the exo-Earth. And then basically on the right, it's convolved, and basically it's how we sample that image and the image plane in the solar gravity lens focal area. So this
from
is
the Einstein ring.
Exactly. So this is what we sample. And essentially what we do is we use our telescope as a light bucket. When we point our telescope to a part of the from a different point in the image plane, we still see the Einstein ring. As we move within the image, the brightness of the Einstein ring changes because we sample different parts of the exoplanet, and we actually record that brightness. So each time telescope sees Einstein ring, when it moves in the image plane, the brightness of that ring changes. When it moves next to adjacent pixel, the brightness changes once again, and so on and so forth. So our observable here is the brightness and the position of the spacecraft with respect to sort of central optical axis. Once with this data, we actually will collect that image, and it will look like the one on the right. So just the brightness data. Now on this chart, what we do, we applied image reconstruction technique, and you see the blur is removed, and we can see that reconstruction is quite impressive, actually.
Yeah, I can see Florida in there. Sorry.
California is in cloud here, so
yeah. Good. Okay. Well, that's okay. So wow. All right. There's a lot there to digest, and I want to get to a couple of comments here because they're relevant to this particular moment in the Hangout. So I want to remind everybody you're watching a Future in Space Hangout sponsored by the American Astronautical Society. So please consider becoming a member. Link is down in the description box. I hope that that you'll consider joining because they've got this as a chance. This is one of the things that they do in their membership. So it's definitely worthwhile doing. And and we are looking at your comments on YouTube, Twitter, Twitch, and Facebook. I'm looking on all the Deep Astronomy channels on all of those areas. So please leave comments. I'm looking at the chat now. And so PCL is asking, so can the telescope be anywhere on the focal line in that figure?
Absolutely.
Let's go back to that.
Starting from 547 astronomical units, we can potentially observe that Einstein ring. For example, if we observe not the exoplanet, but its own host star, the magnified light of the host star will be much brighter than the solar corona. It will be still a tiny bit dimmer than our sun observed with the telescope, but it's about 10,000 brighter than the solar corona. So potentially we don't really need the coronagraph to observe the magnified light from the host star. But because we deal with exoplanet and its light is somewhat dimmer, we need the coronagraph. And so, but for coronagraph to work best, we need to have the Einstein ring separated from the age of the sun. The further we travel from the sun, starting from 550, let's say when we already at 650 astronomical units away, our Einstein ring is separated from the solar surface just nicely, just enough for us to begin observations of exoplanet. Remember, we can observe host star right away once we reach the focal area. But for the exoplanet, we need to move further once we can actually have the Einstein ring separated, and we can remove the contribution from the sun and start seeing the sort of the light Einstein ring from the exoplanet.
Okay, and I got another. Go ahead, Lou.
No, go on.
And then we basically move on. Let's say maybe to 1500 EU. And it will be limited by the resources on board of our spacecraft, because communication, we need to design a system that will be operational at long distances. So now, just put it in the context of reality, right? So this is simulations and science, but now we need to put this in realistic context. What do we have today? Can we travel there? What will be realistic limits? So from the physics standpoint, the light will be there to collect. So we can go all the way to 1,500, maybe to 2,000 astronomical units. But now the sort of reality comes in. And so this is where we need to sort of consider what systems do we have, what technology do we have to enable this mission.
I'm dying to get to that part of it because there's a lot of challenges right in that part. But I want to first of all thank Launchpad Astronomy. Christian, thank you so much. He wants to know if you can tell us how we put a telescope out there in the first place. So that's a good segue into what you were just saying. I mean, we're talking about things on order of where the Voyager spacecraft are right now, and right now, as I understand it, they are communicating via the Deep Space Network, and they're very feeble signals. You're going to need, it seems to me, like a lot more bandwidth and capability than we currently have for things this far away. So get to Christian,
you're not where the Voyager spacecraft is. That's, as Slava pointed out, it's around 140 AU now. We have to get out to be working out. We have to be working out around 600 or 700 AU. The technology that got us the Voyager spacecraft was interplanetary spacecraft and a launch vehicle and gravity assist with Jupiter and Saturn giving you the extra momentum to be able to get out that far. But it still took some 40 years to get to that kind of distance. And what we're trying to do in this project is, of course, to do it much faster and not use that kind of technology. So basically, this interplanetary concept is being enabled by small sats being able to propel smaller spacecraft much faster using solar sails, which I'm sure we're going to get into.
Okay, good. So that's the 1 meter scale. That's reason for the 1 meter scale.
That's right. Yeah, you want to do a smaller spacecraft, which of course we've had now a decade or more experience now with small sats and CubeSats and other small spacecraft being developed. We've even had a couple of interplanetary small sats used by JPL and the Marco mission. We've had solar sails fly. We know we can put these two technologies together in order to fly out to distances of 600 AU in less than 20 to 30 years.
And realistically, I guess what we would like to have a mission completed within the lifetime of a scientist.
That's always the thing that narrows us, right? It's like
a psychological limit to design the mission that will be done in the next 200 years. Probably will not get an interest from the community for that.
But because that's a little bit, multi-generational science missions aren't necessarily something we look into all that much. I remember feeling sorry for the New Horizons guys, right? Who started their career building the New Horizons probe to Pluto, only to have to wait 9 years before the thing got there. This is a different beast altogether.
The history of humanity knows.
Thank you, Christian.
So the history of humanity knows those projects. So we have Great Chinese Wall, we have the pyramids of Egypt, we have other projects, but they were done under very different conditions, so to speak. So funding
motivation
was different.
I don't think you want to sell it that way, Slava. I don't think you want to say, "Hey, we're going to do this like on an Egyptian pyramid scale."
Exactly. So
I don't. I don't think that'll get a lot of funding. People will be like, "What?"
But the point here is that we are faced with the challenges, or maybe a very exciting problem, to really contemplate to design a project that can be done within a realistic time frame. And so realistic time frame is maybe, let's say, 30 or 40 years, given the scale. We have never done this before. We just accidentally, Voyagers are that nice. And so that actually suggests that we need to look at the technologies, the propulsion technologies. And Christian, thank you for bringing this topic into the discussion. It's Christian Reid is a good friend.
Yep. So Launchpad Astronomy.
Yeah, the thing is, when we started looking at the project, initially I was a little bit, I was going all chemical.
Oh shoot!
That bringing the chemical propulsion in the mix limits the capabilities. And so realistically, the only way we can get there in sort of in realistic time frame is using the sun again as a propulsion mechanism. So essentially, there is a momentum transfer when the solar photons emitted by the sun impact a sail, like the spacecraft with a flat sail. And so essentially, that momentum transfer accelerates the spacecraft to very large velocities. And we are talking about, depending on the materials that we will use and depending how close we get to the sun, we are talking about the velocities of 20 to 30 astronomical units per year. And just for the sake of comparison, New Horizons that we discussed, right? New Horizons was able to reach velocity of roughly just about 3 astronomical units per year. So we're talking right there, a factor of roughly 10 increase in the velocity. And so we can do this. The sun is out there. And as Lou mentioned, it's all enabled by miniaturization of spacecraft and the agility of new space industry that is now standing on its own and building and bringing very lightweight, very capable small sats. So putting these small sats in the mix and using maybe some sort of in-flight assembly, so potentially we can build structures in space. And that is something we have done on the ground. We are designing it to do it in space. Next step is really to propel the spacecraft with the large solar momentum transfer, and then assemble the larger spacecraft and move it anywhere we want to the distance we want. So what is left is communication and power. And communication and power, I think optical communication, laser communication, I think is the key. Higher data rate and the more reliable systems that are now in the sort of built and flown. And the power, I think we have to rely on nuclear power. Although, we have some complexities, political complexities of flying the nuclear power in space, but potentially there are some developments that we can benefit from and essentially enable those missions.
So I'm showing, as you were talking, some of these graphics that you had where we're talking about getting out to 550 AU in decades, not centuries. And I had the solar sailcraft architecture that you had outlined here.
Let me comment on this. This is wonderful architecture that was designed by our partner company, Explore. And essentially, Explore, together with another company in Southern California, California Lagarde, they decided to go away from planar sails. Planar sails, there's some interesting design features with planar sails, but going in the vane, sort of having a vane design. With vanes, it's now like a sailboat. You can tuck against the wind with a sailboat. You can go towards the sun with the sailcraft, and the sailcraft can go towards the sun in 3 months. We can launch that spacecraft.
Okay, hey, whoa! So you could go against the solar wind
exactly.
with so, but a sailboat does that with Bernoulli principle.
Same thing here.
What really? There is. That's amazing.
Let me correct you, if I might, because it's a common mistake. Not the solar wind. There's no solar wind involved here. The solar wind is 3 orders of magnitude smaller than the solar photon energy.
Okay.
And yes, you tack, and a sailboat, of course, uses the interface between the wind and the water to do the tacking. If you're not, if you didn't have that interface, you wouldn't be able to go upwind, if you will. And so, and here it's the same principle. We use the gravitational, the orbital motion is one of the media, and the solar pressure is the other. So you can actually position your vector to either increase your orbit velocity and go outward, or decrease your orbit velocity and go inward.
Okay, so it's about the orientation between the solar pressure,
and it's basically changing your orbital, your orbit by either going in toward the sun or going outward away from the sun.
Interesting, and the planar, the vane shape makes that happen.
Well, the angle between the vane and the solar the light, the light from the sun, between the photons and the orbit and the vane. So you get your angle of incidence, angle of reflection. So you point that in the direction you want to go.
And it's really a complete analogy with the sailboat. That for the sailboat you need to have sail and the rudder. In the sailcraft case, we have the solar radiation pressure that plays the sort of the role of the wind, right? In this case, and we have sort of reaction wheels, the momentum that is kept on the attitude control system. So it's plays the role of a rudder. So with this, we can be launched at C3 equals 0, essentially with the deployed from the ride share. We, as a small spacecraft, we take a ride share opportunity and we fly to Earth orbit, or maybe even higher, going maybe cislunar environment, and then we unfold sails, and in 3 months we are going by the perihelion. And so going by the perihelion, essentially, after that, we just position spacecraft and get it most optimal orientation of the vanes with respect to direction that we need and the sun. And here we go. So that's what is enabled. And so the key here is to be able to get as close to the sun as possible. And so here is the new materials that were designed that will enable very close proximity to the sun. With the present sail materials, I think we can get, 25 solar radii? But we can get even closer, maybe 20, maybe 15. And so the closer we get, the faster we go outside the sort of away from the sun, in any direction. And oh, by the way, we can fly any inclination, not only in the ecliptic plane. We can go outside the ecliptic. So
okay, now you're getting where my next questions were going to be about limitations of our field of view. Where were we going to be able to look? And now you're saying we're not limited to being in the ecliptic plane or the
solar sailing is enabling technologies and technology in many ways, because we are not limited by the ecliptic plane as with chemical propulsion. So
that's
here
the line. That's the plane, by
the
way, of the solar system. For those of you who don't know, that's where all the path of all the planets tend to rotate within a few degrees of the sun. So, and you can go well out of that without it, because Voyager got where it was going with the help of gravitational assists from all the different planets as it was heading out. But you're saying we can just put this thing somewhere in some orbit, even to the north rotational pole of the sun, and head out that way if we want to.
And let me emphasize one thing. I think it's very critical, is that in the past, solar sailing ideas were kind of looked upon, oh, well, it's a nice thing to have. But basically, the spacecraft miniaturization, the new electronics that is now available for packaging in a small spacecraft form factor, and also communication that is now in a sort of developed in multiple networks. We can fly a much smaller spacecraft with the solar sailing, and we can essentially use solar sails in multiple ways. For example, we can use them as a radio antenna. For example, just putting sort of some diodes on the antenna and forming it in the shape of parabolic shape. We can repurpose the sails and use them for communication as well. And so the sail idea actually is multifaceted, not only for propulsion, but also to enable multiple capabilities that actually now are being developed by the industry and brought into the NASA reality as well.
Okay, well, I like the idea of getting a ride share out to. I'm sure Elon. He and I go way back. I'll call him and say, hey, let's put one of these meter class things out there. What about sitting somewhere at the L2 point? It seems like all of these missions at some point involve the L2 point. That's just what I'm hearing all the time. So we could launch up there, sit at the L2 point for a while, and then start our trajectory. Is that?
It might be a good idea, but realistically, look. A mission like that, to start a mission like this, probably we need to have some good target to look at, right? To start with, and so once we have from the astronomical community a pointer where this exoplanet presents an interesting target. So there's some presence of atmosphere. There's some interest in it orbits its host star in a habitable environment. So it's a potentially habitable planet. Then we can go.
Tony, you were making a joke about calling up Elon and getting a ride share, but we did that actually. The light sail spacecraft that the Planetary Society flew in, which project that I was fortunate to be able to start a decade ago, we actually did get a ride share with Falcon to launch. Elon was on the board of directors of the Planetary Society in the early 2000s, and so yeah, maybe we can make another phone call.
Why not? Yeah, I mean, you guys are way better connected. I was kidding because he doesn't know me from Adam, but you guys, yeah, so for sure. And I think this is the kind of thing that would be more possible as these commercial rockets become more capable as they are, and certainly a lot less cheaper. So brings the
and
cost of emissions
more
down.
possible, and both from the point of view of rockets and also from the point of view of cost. Obviously, if you can build a smaller spacecraft in this fashion, and you can build multiples of them for exploring. After all, as Slava mentioned, there's already hundreds of putatively habitable worlds out there to investigate. The cost will come down for any of these individual investigations.
Look, when Starlink is flying 40,000 spacecraft, right? So spacecraft becomes a commodity. The cost of the spacecraft is less than $1 million in a sense. So we're talking about reducing the cost of the exploration of sort of livable worlds by orders of magnitude. Potentially, this is what is enabling the whole activity.
Yeah, just don't get me started on Starlink, because I'm not quite sure how I feel about that. But yeah, you're right though. I get what you mean. So let's get to some more comments here. In terms of, this is from PCL on YouTube. In terms of slowing down to align with focal line. In terms of slowing down and to align with the focal line, what kind of attitude control is required? From the NEA Scout Lunar Flashlight design experience, we know solar sail has attitude control problems. I also have an attitude control.
Yeah, actually, we don't have to slow down to get on the focal line. You're going to be flying out on a hyperbolic trajectory, and all you're doing is constantly steering so you match up along that focal line. And you don't want to slow down, actually. You want to continue outward on that. So there won't be anything like that required. In terms of the whole attitude control problem, yes, that's a major issue, of course, in trying to control any craft, solar sail or otherwise. And I think our experience with the solar sails, the two that have flown now, Ikaros, the Japanese solar sail that's flown out on a trajectory from Earth toward Venus, and the light sail, which has now been in orbit for over a year in Earth orbit, which is kind of the worst place to have to use attitude control to do a solar sail. Both have worked rather well. I've actually been surprised, even with all the experience I had on this, to find out how well the sail held up and how we were able to continuously control it by just the tilting of the angle and changing that angle I mentioned before between the sunlight and the sail. So I think attitude control is a very manageable problem. It's not the one that I think is the big one to worry about.
And also, I guess, without going much into details, characteristic accelerations that we are looking out there are microns per meter square. I mean, microns per second square. So this is very well managed by ion propulsion that we have. So
but the ion propulsion that we're talking about is really the supplemental. It's you mentioned nuclear power before. Voyager, of course, has nuclear power, RTGs on board. We're talking about the same scale, maybe even lighter weight than that, for the kind of things we would be using, and we'd be using micro thrusters to do the maneuvers that Slava mentioned to sample the pixels in the Einstein ring.
Right, but it seems to me like a big power use of this spacecraft would have to be in communication, right? You're talking telemetry and bandwidth issues that are way bigger than anything that's been used so far. So,
well, you have a lot of time, so you can have just a few bits per second. You have lots and lots of seconds to get the data back. So it's really it's a manageable problem.
And also, we don't have to bring every bit of data down to the ground. We can pre-process the data on the ground and in flight on the system. And so we are not talking about bringing everything down.
Yeah, so, just don't put one of those 386s on it, like you always hear about, right? We're launching all these probes where, like, our iPhones have more computing power than the spacecraft themselves. So, and there's a reason for it, I get that, but at the same time, we want to make sure we put some decent computing power on there as well, and some storage.
It's an exciting problem to deal with. It's really, we are looking through every realistic piece of technology that may be used here. We are looking at longevity, at the performance characteristics of these instruments, and the ability to communicate and process the data, survive the long flight. We're talking about getting there. It's about 20 years to get there. And so
let me return to that question you had about the whoever asked the question about using the attitude control to stay maintained along the focal line.
Right.
The solar sail won't be working out at 550 and 600 and 700 AU. There's no sunlight there, not enough sunlight there to be using it. At that point, you will be using the microthrusters.
Okay.
And maybe just a few points on without going into details. We will use the light from the host star to establish local reference frame out there, so that we'll fly a spacecraft that will once they reach, let's say 547 AU, the light from the host star will be visible. And that light can be used very effectively to position the optical axis of the host star. We know where the host star is. And then with respect to that knowledge, we'll just move in and out to find our exoplanet and to be with the exoplanet, because nothing is fixed in the universe. Everything is moving. So we need to be sensitive to the proper motion of the system, to orbital motion of the host, of the planet around the host star. Even our own sun is not fixed with respect to the center, to the very center of the solar system. All of that is now taken care of by the mission design and attitude control and the sort of navigation in the focal plane. It's an exciting problem that we addressed, and I think it's solar gravity lens offers a very interesting solution there. Yeah. So SGL helps us to navigate with respect to the magnified light of the host star and really transfer that knowledge to the position of the exoplanet.
Okay, let me get to a question from Frederick Rhodes on Facebook. He's asking, does the solar gravitational lensing use the curvature of the solar magnetic fields enclosing our solar system at all? This is a gravitational effect, isn't it?
We use gravity only.
Right. That's a good question, though. And if they were ionized, if the gravitational waves were ionized, maybe the magnetic field would come into play. But no. Let's see. From PCL, he is asking again, can spacecraft components last 50 years without reliability issues? There's the rub, right? I mean, we kind of got lucky with Voyager. It's still more or less running.
Well, we didn't get lucky. We got well designed. And it wasn't an accident.
Now there's always the nominal mission length and then what you get, right?
Well, that's quite correct. Voyager was designed for a much shorter time, but it's lasted very well long. So it's also been true, by the way, of the Mars rovers, and they're working on the hostile environment. Yep. The surface. They're designed for 2 years. They last for 10 years. Spacecraft in general, space has turned to be a very benign area for spacecraft to work in. It may be hard to get them there, but once they're turned on and it's working, we've had very good luck in exceeding all the predicted lifetimes of spacecraft. Mm-hmm. And yes, it will be a challenge. We have to not only design to last that long, but to design to deal with unexpected issues that come up. You often hear of spacecrafts having to deal with things that have come up. They have to be reprogrammed, or they have to adjust their operating system and that. But we can do that, and you design a robust system to. And I think the 50-year challenge is one that we're starting to meet right now, and we'll certainly be able to meet as we design this mission.
So, all you young career astronomers, keep this in mind, okay? After you get your PhD, this is
and also let me point to one more thing. Once we since the beginning of space era, we would be flying a single spacecraft on a single mission, and basically we become very risk averse because we don't want to lose this mission, and so that's why a lot of effort went into engineering, and those spacecraft are done once at a time, single spacecraft. We don't usually refly those missions. Recently, within the last 10 years, we have seen spacecraft development. The developers would put hundreds and thousands of identical systems. So reliability is now addressed by being sort of making many of those systems identical and choosing the best parts. It's like in the computer industry. You essentially you build many chips and you select the best ones. So the same logic now is transferable to the space arena, and we definitely will benefit from it by flying small spacecraft, maybe not single, but several, that will be built identical, and then the best part will be chosen and going out. So I think it's a very interesting sort of bifurcation point in this history of space industry, because now we build many spacecraft and many small agile systems.
Awesome. Thank you. Eric Guerra, by the way, thank you for your support. I appreciate it. He goes, thank you, panel. Great stream. Would an SGL also be able to detect and view interstellar space oddities objects like Oumuamua?
The SGL itself will not be able to do that because we need to know precisely where these objects would be, and also those objects need to emit light or reflect light. So those guys are moving very rapidly. But the technology that we have for the solar gravity lens and the solar sailing in particular will be able to chase up and meet up with those objects when they traverse the solar system. No other technologies can, but solar sailing can. And we actually, once we detect that system, that object come into this in the inner part of the solar system, we can build, we can fly a solar sort of a sailcraft to catch up with that object, sort of interact with that, and sort of take pictures and study it once it's still within the solar system. So solar sailing enables the missions that will have very fast exit velocities from the solar system.
Okay. You guys are giving some great questions. Thank you. William Kammerer wants to know, do you imagine needing to use optical communication to be able to maintain contact over such a vast distance? I think you talked about lasers, right?
Lasers. So, yeah, we were thinking about the architecture, string of pearls architecture. Essentially, there we can fly several pearls, and each pearl will have maybe a couple or maybe 5 small sats working in the solar gravity lens area. And so then only the inter-pearl communication will be needed. We don't really rely on the communication all the way from the pearl to the ground. It has its own challenges. But potentially, if all it's addressed, we can use that. But now the baseline assumption is that we use several pearls and maybe 200 AU between them. And we communicate only, like, let's say, 200 AU between them.
Okay. I'm trying to hurry through these before we run out of time. This is from Joe Kozak. How big is the optical reflector on the spacecraft? For example, magnification. What magnification does the sun do for us? I believe you talked about meter class, but go ahead.
Once you have a meter class telescope, for point sources, magnification is about, on the meter class system, it will be about 1 billion times. So when we talk about resolved objects, the magnification per pixel, for example, it will be about about 1 million times. But then we have hundreds of, maybe thousands of pixels that are amplified. So essentially, it depends on the proximity and the size of the object, but it's much brighter than using it sort of unaided with the SGL. So SGL truly unique capability.
Yeah. It's about a magnification of 1 billion. I'm just kidding. Okay, so John Suffel, good to see you again, man. He wants to know, would SGL be able to detect pollutants in the atmosphere of an exoplanet as a sign of intelligent life? What do they call those? Exo markers?
I would say it will be able to detect a sign of unintelligence. If those aliens would use the carbon fuel as we do, so the signs of unintelligence will be definitely detectable.
Boom! Dissing on them already. We don't even know they're there. All right. Let's see. Another quick question. Could SGL target more than one system by moving to a new focal line?
When you have SLS...
That's a good question.
When you have a SLS camera and you have a very high zoom on your camera, you are training that zoom on a particular target. So as I said, the SGL offers you that sort of zoom capability. So realistically, we'll be limited by propulsion to repoint our instrument to a different target. For now, we are thinking about flying SGL to a single planetary system. For example, when we fly to Cassini, when we fly to Saturn or Jupiter, we study the entire system of satellites of those planets. So with SGL, we will be able to study all 8 planets around, TRAPPIST. We'll be able to study every planet orbiting any host star. So for now, the idea is, because of the limits of propulsion, we'll be studying, it's a single system mission. But then, depending on the cost, if we will be able to make it affordable, potentially each interesting target may have its own mission flown to the optical axis of that target.
Oh boy, guy, you get just so many questions. All right, let's see. Pavel wants to know: is Jupiter too small to be a lens?
It is too small to be a lens, and realistically, the gravitational focusing of Jupiter is around 26 astronomical units out. So it's just 2,600 astronomical units. I'm sorry, 2,600 astronomical units. It's just not feasible to use Jupiter as a lens.
Okay, well, there you go. So wow, I want to thank you guys so much for taking time out to be with us. I'm afraid we are out of time, but our guests today are Lou Friedman. He was the co-founder and the executive director emeritus of the Planetary Society. He's working with Slava Turyshev, who's the research scientist at JPL, who has found a way for us to finally look at these exoplanets and see what's on them. Other space telescopes, JWST is hoping it's got near spec on board. It's hoping to see spectra of some of these atmospheres, but resolving these planets in a way that we can see what's on them is outlined by this solar gravitational lens, which is this is a brand new era of astronomy. We've talked about this since the very first LIGO observations were announced. Gravitational waves are about to be the future of astronomy. I used to say infrared was the future of astronomy, but now we're turning towards gravitational wave astronomy, and it's just and gravitational lensing and all the stuff that's associated with Einstein and his bending of space-time. So, guys, thank you so much for taking time out to be with us. If there's ever a chance to get you guys back, I would love to have that happen because
thank you, Tony, and I thank you for giving a good shout out to Einstein. I think he deserves it.
He does. I mean, a little bit of an overachiever in my book, but
it was nice to be with you. Yeah.
And Tony, maybe just few parting words. This work really was enabled by NASA Advanced Innovative Institute concept. So essentially, NIAC was our primary funder who believed in the technology. It's an early development in the project. We are funded for a year and a half longer. So just stay tuned to the development of this project. Maybe in a year we'll tell you more details as how this project actually will evolve. We are working very hard. We have a very good, diverse team, including Aerospace Corporation, JPL, the UCLA, a group of private industry partners like Explore, and our additional group of we are building private-public partnership to enable the mission in the future. So more interesting topics are to come.
That would be a great hangout too, because we didn't even get to that. What are the specifics? What's the next stage of building this thing, and where are you in those processes? So that's a topic of a whole other hangout. But anyway, on behalf of Slava and Lou, I want to thank you both. Thank you all so much for watching. I want to thank the American Astronautical Society for putting this together. Please go check them out, astronautical.org/members, and thank them for what they're doing and bringing these to you. I'm Tony Darnell from deepastronomy.space. Thank you so much again for watching. And as always, keep looking up.
Yes.